Okay. Now, is this working? Is it working? Is it filming? Are we on? Yeah? Okay. So, this is kind of take two, and we did a little bit of a rehearsal, sort of. That sounds a little weird. Not really, but sort of. I just had to move out of this area to animate this discussion. Ellen, what's the question you had? Say it out loud. Just say anything. You don't have to read out of the book. Just tell me. Talk to me. Yeah, Ellen was wanting to know the main difference between real and ideal gases. So let's talk about that for a minute, okay? Yes? Let's start doing what I was actually starting to do on the board, okay? Is that good? It was pretty good, wasn't it? All right, now, I'm a terrible artist, but let me try this. Okay, I have 2 flasks of a liquid. Okay? I have 2 flasks of a liquid. And those liquids are full. You know, they're completely full right up to that line. Okay? Those are liquids, yes? Okay, now, I'm going to put a tube, a glass tube, through the liquids. Through the top, down into it, okay? Okay, and they're both at the same temperature. They both have the same temperature, yes? Yeah. And they have the same volume, correct? Constant pressure, yes? Okay, now, so we're going to heat both liquids a few degrees, and we're going to see what happens. Here is what the tube looks like in the cork. You really can't see that, but we're pretending we can. It's going through the cork. And this liquid only goes to right here. Only goes to right there. Comes up through it and only goes to right there. Okay? This one goes up to here. Almost comes out. So which liquid expanded more? A, right? Okay, now. I introduced to you, but we didn't spend a lot of time on it. In physics, we will. It's called the expansion of liquids, and you can actually calculate the coefficient of volumetric expansion. It's called beta. It's beta, as opposed to alpha, which is linear for solids and that expand linearly. So you can actually calculate, that's a regular B, you can actually calculate the coefficient of expansion for both of those liquids. You could come up with some kind of experimental design, and you can identify those liquids just by calculating the coefficient of expansion. Those liquids have different physical characteristics, don't they? They are physically different in their behavior, are they not? Yes or no? They are physically different in their behavior because of intermolecular forces. Can you look up? Oh, did we ever find out about Pascal?
He was named after some French scientist.
And what was his name? What was his first name? I'll give you a hint. Hiking down a trail. What do you do to the tree to mark your trail so you don't get lost? Either with some environmentally friendly paint or... Blaise Pascal, that's actually quite correct. What a great name, Blaise. There was a dog, a collie, in my neighborhood when I was a kid, called him Blaise. Love that name. If I ever had a child again, I'd call them Blaze. I like that. I like that. A boy or a girl, Blaze. Yeah. So anyway, what was I saying? What was I saying? I completely lost my train of thought.
Marking the trail.
Yeah, but before that, all of a sudden I went off. Oh, I know. Can you name the 4 intermolecular forces?
Dipole,
Dipole,
dispersion,
dispersion, hydrogen bonding, and ion, right? Okay? So, these molecules are close together. So, the molecules, which have different chemistry, when they're close together, as an individual chemical, they're going to behave uniquely. For instance, what does water have a lot of? In spades. What does it have? What does water, which intermolecular force does water have a lot of? What is it? Hydrogen bonding, right? Hydrogen bonding has a lot of it. Anything made of hydrogen, carbon, any hydrocarbons with oxygen is going to have a hydrogen bonding, like laundry. These wrinkles, it's hydrogen bonding, right? Hydrogen bonding. I like to demonstrate hydrogen bonding. I love my hydrogen bonds. Love them. I wear as many hydrogen bonds as I can. Yes? If you make material without hydrogen bonding, some kind of synthetic material, you don't have a lot of wrinkles, correct? All right, now. So water is held so closely together, it takes so much more energy to get the vapor pressure equal to atmospheric pressure, correct? Doesn't it? So it'll boil 20 degrees higher than alcohol-ish because it has more hydrogen bonding, because they're closer together. The closer the molecules are together, the more uniquely the group of molecules will behave. Well, that sounded good, didn't it? That sound good or what? Now, let's say that in terms of the kinetic theory of gases, where we're talking about molecules like this, molecules like that, where there's not very many intermolecular forces, right? They're pretty generic, right? They're just gases, they're simple diatomic molecules, right? And they are far apart, they're in a gas, they're moving very quickly. And let's say I have hydrogen here. I have hydrogen gas and I have nitrogen gas. And I heat them. And I somehow can identify the change in volume of the gas. Somehow. I set it up experimentally. And hydrogen expands to right here when I heat it. Okay? Right? Charles' law, temperature and volume. And within a certain set of conditions, like between 273 and 373 Kelvin, I heat this just a few degrees and it goes to right there. Where is the nitrogen going to end up? Now it started off the same volume. Heated this a few degrees, it went to right there. Where's nitrogen going to go? Where is nitrogen going to go? Ellen, it'll be the same. Why is it the same? You don't have the intermolecular forces. The molecules are moving fast. They're undergoing elastic collisions. They have, physically, are gases at room temperature physically the same? Yes. You can't tell them apart physically. You can't. They may have different odors, but odor, again, is a chemical reaction. They may behave differently in terms of chemical behavior, but those are chemical properties. Physically, are they pretty much the same at room temperature? Yeah. They act ideally. But now, if I take these gases, this is the gas at room temperature. They're far apart. They're moving very quickly. If I compress them, they're still a gas, but I compress them, they're closer together, aren't they? Now, all of a sudden, there may be some intermolecular forces involved, right? So they're going to lose some of their anonymity. They're going to gain some identity. So these gases will behave in an ideal manner because they're far apart. Kinetic theory of gases, elastic collisions, yeah? No intermolecular forces involved, but they become compressed. High pressures, weird temperatures, strange conditions. All of a sudden, they behave in a real manner. They gain some identity. They lose their anonymity. Not good, correct? Are we cool? Are we good? Is there anything you want to add? Is there anything I forgot? Yes or no? Mark, how you doing over there, all right? The man from Texas. Excellent. Did you? Oh, we named the four intermolecular forces, correct? Excellent. When we do solution chemistry, we're going to be using those intermolecular forces all the time to find out if something can dissolve. Clear? A really cool example is soap. Why is soap so cool? You want to know why? It's really cool. Soap is a long chain fatty acid. That's what soap is. Okay? Okay? This is it. But this side is nonpolar. This is going to be cool. That's nonpolar. I'm not going to be specific, but that's nonpolar. That's nonpolar. This side is polar. This hooks onto the fat, the grease, the grime, the stain. Like dissolves like. Did you ever hear it? I don't like the octet rule. I hate that rule. But like dissolves like, excellent rule of thumb. Excellent. Like intermolecular forces dissolve like intermolecular forces. That's going to be ionic. Is that going to attach to polar water? You bet. That attaches to the stain. That attaches to the water. Easy. Cool or what? It's all intermolecular forces. The study of gas laws is the study of intermolecular forces that don't really involve themselves in the day-to-day life of gases at normal conditions. We're off.